In this video, I'd like to introduce a concept called the adjoint and then see how that's related to inverses and determinants. So, take a look here at the cofactor expansion of the determinant. This was the definition we gave earlier. This is essentially expansion across the first row is what I have written here. So I have the entries of the first row, A11, A12, A13. Each of those is multiplied by the corresponding cofactors, C11, C12, and so on. Notice that the cofactor is, of course, a minor times plus or minus 1. So I've written these all as plus signs, but every other one is minus. And this cofactor would be multiplied by plus 1, this one would be multiplied by minus 1, but that plus or minus 1 is built into the cofactor itself. There's a curious thing that happens if we mismatch the rows and the cofactors. And this did come up in an earlier video, but I want to take a look at it again here. That if instead of doing entries in the first row times cofactors of the first row, what if I did, for instance, entries in the second row times cofactors in the first row? So entries from one row, cofactors from another row. What happens? Well, let's just do an example here. Here's a 3 by 3 matrix. The determinant is, so I'm going to expand across the first row. There's the 1, 2, 3. And then the cofactors, the first cofactor is that little subdeterminant. Second cofactor is the 4, 6, 7, and 10, but with a minus sign. And then the third cofactor here would be 4, 5, 7, 8. Take that 2 by 2 determinant. And it turns out the determinant of this thing is minus 3. Now, I'm going to use the same cofactors. So this is the cofactor 1, 1, the cofactor 1, 2, and the cofactor 1, 3, with the minus sign there. But the entries that I'm going to choose now are those things in the second row. So 4, 5, and 6. 4, 5, and 6. And what I get is 0. Try it with the third row. So again, same cofactors, same 2 by 2 determinants there. But instead now of the second row, I'm using the third row for these entries. So the 7, 8, 10, 7, 8, 10, and I get 0. Coincidence? No, it is not. Consider the following two determinants. 4, 5, 6, 4, 5, 6, 7, 8, 9. Is it obvious what that determinant is equal to? Hope it should be, because it's got two rows that are equal to each other. And one of the things we know about determinants and row operations is if you swap two rows, you multiply the determinant by minus 1. But if I swap the first two rows of this thing, you can't tell I swapped them. So multiplying the determinant by minus 1 had better give me the same answer that I had to begin with. And are there any numbers you know of where multiplying by minus 1 doesn't do anything? There's only one such number, right? 0. So the determinant of this thing has to be 0. Likewise here, this one is 0 because the first row and the third row are the same. Okay. Now my claim is that this first determinant, if I took this by the cofactor method, it would look exactly like this set of calculations right here, because I'm using the first row, 4, 5, 6, and the cofactors from the first row. Likewise, the determinant down here with the 7, 8, 10 on the top, doing this, expanding across the first row to find the determinant, would look exactly like this calculation here. So these two calculations are doing determinants where two of the rows are the same. So if you were to take any row and expand with cofactors of another row, you will get 0, because that's equivalent to doing a determinant with two equal rows, and that has to be 0. Okay. Now let's give a couple definitions here. Given any n by n matrix A, we define the matrix of cofactors like this. So if A is n by n, the matrix of cofactors will also be n by n. And the entry in the first row, first column is the cofactor from the first row, first column. The cofactor, sorry, the entry in the second position there, row 1, position 2, is the cofactor for row 1, column 2, and so on. So each position in matrix A has a corresponding cofactor. If I calculate all those cofactors, then I get this thing called the matrix of cofactors. Okay. Now, what I really want to define is the adjoint. and the adjoint is the transpose of the matrix of cofactors. So if you take a look at the difference between the matrix I have here and then the matrix I have here as the adjoint of A, and this is sometimes just abbreviated ADJA, adjoint, is that what was the first row up here is now the first column. So this is the cofactor from row 1, column 2. This is the cofactor from row 1. Sorry, this is row 1, column 1. This is row 1, column 2. But it's in the position of row 2, column 1. Likewise, this one here, this is the cofactor for row 2, column 1, but it's in the position of row 1, column 2. So this is just the transpose of the matrix of cofactors, and this is what's called the adjoint. Okay. So here's a couple of examples. I've got a 2 by 2 matrix here, just 1, 2, 3, 4. The matrix of cofactors. Matrix of cofactors in the position 1, 1. I want the cofactor 1, 1. So cover up row 1, column 1. That leaves 4. In the position 1, 2. So row 1, column 2. Cover up row 1, column 2. It leaves a 3. Because 1 plus 2 is odd, I need to multiply by a negative 1 there. So it's negative 3. Likewise, in the position 2, 1, cover up the second row, first column, it leaves a 2. Again, I need a minus 1 here. And then in the second row, second column, cover all that up, leaves a 1 left over. So the matrix of cofactors is that. The adjoint then, of course, is the transpose of that. So the 4 and the 1 stay in the same place. And the minus 2 and the minus 3 swap places there. Now, one of the things that happens quite often when I'm teaching this in a face-to-face setting is that quite often students will recognize that, hey, I think we've seen something like this before, haven't we? Where, what did we do? We swapped the 2 things on the diagonal and we made the other 2 things negative. Ring a bell anywhere? Well, maybe it does. Maybe it doesn't. We'll discuss it here in just a moment. Here's another example. Let's take this 3 by 3 matrix and find its adjoint. Okay, so here we go. First, the matrix of cofactors. So in the first row, first column, this right here, I need 50 minus 48. That's a 2. In this position, I need 40 minus 42, which is negative 2, but then I can multiply that by negative 1, so that's a 2. In this position, I've got 32 minus 35, which is negative 3, multiplied by plus 1. This position right here, so this position right here, I'm going to do a 20 minus 24, which is negative 4, but this is in an odd position, so you multiply by minus 1 to make it a plus 4. In the middle, cross out second row, second column, I've got 10 minus 21, which is negative 11. Over here, I've got 8 minus 14, which is negative 6, but it's an odd position, so that's the negative becomes plus. Down here, it's first row, third column, third row, first column, which is even. 3 plus 1 is even, so I'm going to multiply with plus 1. But cover up those row and the column, leaving 12 minus 15 is negative 3. This position, we've got 6 minus 12, which is negative 6, but it's in an odd spot, so multiply by negative 1, you get plus 6. And finally, in this corner over here, we've got 5 minus 8, which is negative 3. There's the matrix of cofactors, which take the transpose to get the adjoint. This is almost a symmetric matrix. The only thing that happened is the 2 and the 4 swap. But anyway, there's the adjoint. Well, you might be wondering, why do we care? Well, we care because this is actually a really nice way of coming up with the inverse of a matrix. Notice, if I take each of these 2 examples and multiply the matrix I started with times the adjoint that I just had, we get the following. So here's the 2 by 2. So here we go, first row, first column, that's 4 minus 6 is negative 2. Second row, first column would be 12 minus 12, that's 0. First row, second column, That's negative 2 plus 2, which is 0. And second row, second column, second row, second column. There's a negative 6 plus 4, which is negative 2. And notice that this is just negative 2 times the identity. By the way, what was the determinant of this matrix? 1 times 4 minus 2 times 3, it's negative 2. So what I got was the determinant times the 2 by 2 identity. Likewise, take a look at the 3 by 3 times its adjoint. Now these are a little bit bigger calculations, but here we go. First row, first column. I've got 2 plus 4 minus 9. 2 plus 4 minus 9. 6 minus 9 is negative 3. There we go. Here we go. The next one down would be 8. 8 plus 10 is 18 minus 18, which is 0. And you can follow it through. I get this, which happens to be negative 3 times 3 by 3 identity matrix. Remember, the determinant of this matrix that we calculated has 3. Actually, we count as negative 3. So what I end up with is the determinant times the identity. And this, indeed, is a theorem that if I have any square matrix whose determinant is not 0, then the inverse of that matrix is 1 over the determinant times the adjoint. Now to prove this is, just a bit of following the things through, but how do I prove that the inverse of A is given to that? There's homework questions like this too. It says, show that the inverse of some matrix is something else, and they give you the something else. They don't say find the inverse. They give you it, and they say, show that this is the inverse of the thing I started with. Well, it's like saying, show that 1/7 is the multiplicative inverse of 7. It's like, well, just multiply them together and see that you get 1, right? So in this case, what I need to do is I need to show that if I multiply A times this thing, I get the identity, which means A times that thing is the identity, so that thing must be the inverse. I want to show that if I multiply A times this thing, I get the identity matrix, which would show that this is the inverse of A. So if I multiply A times, the 1 over det A is just a number. So this number times this matrix, I have properties of matrix multiplication, which say that I can multiply the matrices together first and then just multiply 1 over det A afterwards. So now just putting everything in here, of course, matrix A is just A11, A12, and so on. This is the entries of matrix A. And the adjoint of A is, of course, the transpose of cofactors. So this is what we had for the adjoint. And now I'm just going to do the multiplication. So I have A1, so the first row, first column, which is going to give me the entry here. First row, first column, I got A11, C11, plus A12, C12, and so on, all the way down to plus A1n, C1n. Well, that's exactly the determinant. It's the first row multiplied by the cofactors from the first row. Remember, the adjoint here was the matrix of cofactors transpose, so this column is the cofactors from the first row. Okay? So that's just the determinant. Likewise, if I do the second, to get this position here, second row, second column, use the second row and the second column. These are entries from the second row of A times the cofactors that come from the second row of A. So that is, again, the determinant. And all the way down that diagonal, what you're getting is the determinant expanded across the ith row for the first row, the second row, all the way down to the nth row. Now, any other position, so for instance, the second row, first column, I'm going to use the second row here and the first column here. So this would be these entries from the second row, each multiplied by cofactors from the first row and added up. But that, we saw above, was always equal to 0. So every single other entry in this matrix is 0, except the diagonal, and the diagonal is all just the determinant. So if I multiply this now times 1 over the determinant, I'm going to get an identity matrix. So A times this stuff is equal to the identity. That means that A inverse is equal to this stuff. Okay? 1 over the determinant times the adjoint. Let's take a look at a couple of examples here. The first example is, where am I? The first example is just a 2 by 2 matrix, and actually Remember early in the video I said, where have we seen this before? This is where you've seen it before. We have a formula for calculating the determinant of, not determinant, the inverse of a 2 by 2 matrix. And it was that the inverse is 1 over AD minus BC, which is the determinant of that matrix, times this thing. Remember we just said swap the A and the D, change the sign of the B and the C. Well, now we know that this 2 by 2 matrix is actually the adjoint of the one that we had here, right? That this is the cofactor 1, 1, this is the cofactor 2, 2, this is the cofactor 1, 2, and the cofactor 2, 1, the adjoint. I had a student many years ago when we did that 2 by 2, I was like, oh, I wonder if I could come up with a way of doing the 3 by 3. So before we'd even done adjoints, he worked and came up with a formula that was really seemingly cumbersome. But once you see that it's just the adjoint, we can actually, as long as the numbers aren't too crazy, I can do these in these 3 by 3 inverses in my head. But here's the one we had: 1, 2, 3, 4, 5, 6, 7, 8, 10. The determinant of that thing was -3. We calculated it up above. So 1 over -3, I'm calculating A inverse now. And now I just have to do the cofactors in the appropriate places to get the entries here. So first row, first column, cover up the first row, first column. The little 2 by 2 determinant I need is 50 minus 48. Now I'm going to work my way across the row, but I'm going to work my way down the column, right? Because I'm doing the transpose. So in the first row, second column, I'm going to use the second row, first column cofactor. So cover up the first row and the second column, giving me 20 minus 8 times 3 is 24, 20 minus 24, but then that has to be multiplied by -1. Likewise, in the first row, third column, I'm going to use the third row, first column, cover the third row, cover the first column. I've got 12 minus 15, right? And that would have a plus sign. Likewise, the second row here, I'm going to be working my way down the second column. So first row of the second column, cover that up, 40 minus 42 with a negative sign. And then in the middle here, cover those up. I've got 10 minus 21. And lastly, over here, I've got 6 minus 12, but with a minus sign. And then, of course, the third row would be getting the cofactors of the third column. And I end up with this matrix right here, which is that. So I could do that. I could do that inverse without using my calculator and without having to do a whole bunch of row operations to do it. I could just do the adjoint. Now, although this worked reasonably well for a 2 by 2 and a 3 by 3, this gets really, really hard to calculate for bigger ones. I mean, I can even just go to a 4 by 4. Each of the cofactors is a 3 by 3. So each of these calculations here would be, 3 2 by 2 determinants. And if you had to do, 5 by 5, then you're going to have 25 4 by 4 determinants that you got to do. And this gets to be a really big calculation. So in general, we don't use this to calculate inverses. However, what this does is it gives us a very precise formula for each entry in the inverse matrix without relying on row operations. I mean, I know that the entry in the second row, second column is going to be the cofactor 2, 2 divided by the determinant. I know that the entry in the position, what's this, first row, third column is going to be the cofactor 3, 1, so third row, first column, right, divided by the determinant. So I have a formula for each entry if I need it. Not the way I would typically calculate it, but it gives me a formula if I only need one entry at a time. If I need the whole thing, yeah, row operations is probably the way to do that, calculate that inverse. Okay. In the next video, we will actually look at using this notion that we can do individual entries to help us solve systems of equations.